Preparing for a software engineering at Google interview, you've reached Interview Guide, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How do you approach optimizing a brute force algorithm during a Google coding interview? I start by naming the brute force solution because it proves correctness. Then I identify the bottleneck. For example, duplicate lookups often turn O of n squared into O of n with a hash set. I also discuss space, not just time, because Google interviewers care about trade-offs. Finally, I validate with edge cases like empty input, duplicates, sorted data, and maximum constraints before writing code. That makes the optimization deliberate rather than lucky. While answering, focus on communicating your thought process, starting from brute force, identifying bottlenecks, choosing better data structures, proving complexity, and validating with edge cases before coding. Question 2. Given a string, how would you find the length of the longest substring without repeating characters? The core idea is a sliding window with a map from character to its latest index. I move the right pointer through the string and advance left only when a repeated character appears inside the current window. Each character is processed at most twice, so time is O of n, and space is O of k, where k is alphabet size. The main bug to avoid is moving left backward on stale repeats. Make sure to cover the sliding window technique, left and right pointers, character index tracking, stale duplicate handling, time complexity, space complexity, and tricky cases like repeated clusters. Question 3. How would you implement an LRU cache with O1 get and put operations? An LRU cache combines a hash map for O1 lookup with a doubly linked list for recency ordering. On get or put, I move the node to the front. If capacity is exceeded, I evict the tail, which is the least recently used item. I call out edge cases like updating an existing key, zero capacity, and memory cleanup. The invariant is simple. Map points to list nodes, never copied values. In your answer, talk about combining a hash map with a doubly linked list, maintaining recency order, eviction logic, update behavior, invariants, and common implementation pitfalls. Question 4. How do you detect whether a linked list has a cycle, and how would you find the cycle start? I use Floyd's cycle detection. One pointer moves one step, the other 2 steps. If they meet, a cycle exists. If fast reaches null, there is no cycle. To find the cycle start, I reset one pointer to head and move both one step at a time. Their meeting point is the entry. This uses O of n time and O of 1 space, which is usually preferred over a visited set. Be sure to mention Floyd's slow and fast pointer algorithm, why it works, how to locate the entry node, constant space, and edge cases like empty lists. Question 5. Given a list of intervals, how would you merge all overlapping intervals? I sort intervals by start time, then scan from left to right. I keep the last merged interval. If the current start is less than or equal to the last end, I merge by taking the maximum end. Otherwise, I append a new interval. Sorting dominates at O of n log n, and the scan is O of n. I clarify whether 1, 3, and pre-5 count as overlapping, because that boundary changes the condition. While answering, cover sorting by start time, scanning once, overlap conditions, updating interval ends, output construction, complexity, and boundary cases like touching intervals. Question 6. How would you return the top k most frequent elements from a large array? First, I count frequencies with a hash map. If k is small, I maintain a min heap of size k, giving O n log k time. If values are bounded or n is manageable, bucket sort by frequency can reach O n. For average linear time, quick select works but is trickier. In a streaming setting, I would discuss approximate structures like count min sketch, because exact top k can be expensive. Make sure to compare heap, bucket sort, and quick select approaches. Explain frequency counting, complexity trade-offs, memory usage, tie handling, and what changes for streaming data. Question 7. How would you find the shortest path in a grid with obstacles? For an unweighted grid, BFS is the right default because the first time I reach a cell, I have the shortest distance. I push the start into a queue, explore 4 directions, skip obstacles and visited cells, and track distance by level or store it with each node. If moves have different costs, I switch to Dijkstra. If I have a target and a good heuristic, A can reduce exploration. In your answer, talk about BFS for unweighted grids, visited tracking, coordinate validation, queue usage, distance levels, obstacle handling, and when Dijkstra or A star becomes necessary. Question 8. How would you search for a target in a rotated sorted array? I still use binary search, but at each step I determine which half is sorted. If the left half is sorted and the target lies between left and mid, I move right to mid -1. Otherwise, I search the other half. The symmetric logic applies when the right half is sorted. With unique values, time is O of log n. With many duplicates, worst case can degrade to O of n. Be sure to explain modified binary search, identifying the sorted half, deciding which side can contain the target, duplicate complications, complexity, and off by 1 safety. Question 9. How would you design an autocomplete system for Google scale search suggestions? Autocomplete is latency sensitive, so I would pre-compute suggestions rather than rank everything online. A trie or prefix index maps prefixes to top candidates, while offline jobs compute rankings using popularity, freshness, location, and personalization signals. The serving path should be cache-heavy and geographically close to users. For scale, I would shard by prefix or language and handle hot prefixes separately. The key trade-off is freshness versus ultra-low latency. While answering, focus on tries, prefix lookup, ranking signals, latency constraints, caching, sharding, updates, personalization, abuse prevention, and separating online serving from offline computation. Question 10. How would you design a URL shortener like goo.gl? I would expose create short URL and redirect APIs. For keys, I can use base62 encoded IDs or random tokens with collision checks. The mapping store needs high read availability because redirects dominate writes, so cache popular mappings aggressively. Analytics should be asynchronous to avoid slowing redirects. I would add rate limits, malware checks, expiration support, and custom aliases. Strong consistency matters during creation, but redirect serving can prioritize availability and low latency. Make sure to cover API design, key generation, collision avoidance, database schema, redirects, caching, analytics, expiration, abuse detection, and availability versus consistency trade-offs. Question 11. How would you design a distributed rate limiter? A token bucket is my usual choice because it allows controlled bursts while enforcing an average rate. For a single node, it is straightforward. Refill tokens over time and consume 1 per request. Distributed rate limiting needs atomic updates, often using Redis scripts or a strongly consistent counter service. I also define the key, such as user, IP, or API token. If the limiter fails, the product decision is fail open or fail closed. In your answer, talk about token bucket or leaky bucket algorithms, distributed counters, Redis or in-memory stores, clock issues, atomicity, fairness, burst handling, and failure behavior. Question 12. How would you implement a thread-safe producer-consumer queue? I protect the queue with a mutex and use condition variables to coordinate producers and consumers. Consumers wait while the queue is empty. Producers wait if the queue is bounded and full. The wait condition must be inside a loop because of spurious wake-ups. I also include a shutdown flag so waiting threads can exit cleanly. The important engineering detail is minimizing lock scope while preserving correctness and avoiding busy waiting. Be sure to mention mutual exclusion, condition variables or semaphores, blocking behavior, bounded versus unbounded queues, spurious wake-ups, shutdown signaling, and avoiding busy waiting. Question 13. How would you shard data across many servers, and what problem does consistent hashing solve? Naive modulo sharding is simple, but when server count changes, many keys move. Consistent hashing places servers and keys on a ring, so adding or removing a server moves only a fraction of keys. Virtual nodes improve balance by giving each machine multiple ring positions. I would still monitor hotkeys because hashing does not eliminate skew. Replication and a routing layer complete the design for availability and client simplicity. While answering, cover hash-based partitioning, rebalancing pane, consistent hashing rings, virtual nodes, hotkeys, replication, routing, and how node additions or removals affect movement. Question 14. When would you choose strong consistency over eventual consistency in a distributed system? Strong consistency is worth the cost when stale reads can violate correctness, such as payments, inventory reservation, permissions, or account balances. Eventual consistency is better when availability and latency matter more, like feeds, view counts, or analytics. I frame the choice around user impact, not theory alone. If I choose eventual consistency, I add reconciliation, idempotent operations, versioning, and clear UX states so temporary inconsistency does not become data corruption. Make sure to explain consistency models, user-visible correctness, latency and availability trade-offs, cap intuition, examples like payments or counters, and mitigation techniques for eventual consistency. Question 15. How would you test a new production feature before launching it to millions of Google users? I would start with unit tests for logic and integration tests for service boundaries. Then add load and failure tests for production-like behavior. Launch should be behind a feature flag, first to internal users, then a small canary, then gradual rollout. I would monitor latency, errors, saturation, and business metrics. A good launch plan includes an instant rollback path. For user-facing changes, I would also use A/B testing carefully. In your answer, talk about unit tests, integration tests, load tests, staged rollouts, feature flags, canaries, monitoring, error budgets, rollback plans, and experiment design. Question 16. A service suddenly shows high P99 latency. How would you debug it? I start by confirming the symptom, which endpoints, regions, and percentiles are affected. Then I check recent deploys, traffic changes, saturation metrics, error rates, and dependency latency. Distributed traces help identify whether time is spent in compute, database, network, or queues. If user impact is high and a recent change correlates, I roll back first and investigate after mitigation. Tail latency often comes from contention, retries, or overloaded downstream services. Be sure to cover checking recent changes, metrics, logs, traces, dependency latency, saturation, queuing, regional issues, rollback decisions, and distinguishing average latency from tail latency. Question 17. How do retries, timeouts, and idempotency work together in reliable service design? Retries improve reliability only when they are bounded and paired with timeouts. I use exponential backoff with jitter to avoid synchronized retry storms. For write operations, idempotency is essential. The same request may be delivered twice, so the server needs an idempotency key or deduplication record. Timeouts should reflect dependency budgets, not random defaults. Without these controls, retries can turn a small downstream issue into a full outage. When answering, focus on bounded retries, exponential backoff, jitter, timeout selection, retry amplification, idempotency keys, duplicate suppression, and safe handling of partial failures. Question 18. Tell me about a time you disagreed with a teammate during a design or code review. I would describe the disagreement objectively, not as a personal conflict. For example, I preferred a simpler design while a teammate wanted a more flexible abstraction. I gathered data on current requirements, likely extensions, complexity, and testing cost. We agreed to implement the simpler version with clear extension points. The result shipped faster and remained maintainable. The lesson is to anchor debates in user impact, evidence, and long-term ownership. Make sure to structure the answer with situation, disagreement, evidence used, collaboration, final decision, impact, and what you learned, reflecting Google's collaborative engineering culture. Question 19. How would you process billions of log events to find the top error messages per hour? For batch processing, I would partition logs by hour, map each event to an error message key, aggregate counts locally, then reduce globally to get top errors. For near real-time, I would use a streaming system with tumbling windows and stateful aggregation. Exact counting can be expensive for huge cardinality, so approximate heavy-hitter algorithms may help. I would also handle late events, duplicate ingestion, schema changes, and durable checkpoints for recovery. In your answer, talk about batch versus streaming pipelines, partitioning by time, aggregation, MapReduce style processing, windowing, approximate counts, late data, storage, and fault tolerance. Question 20. How would you serialize and deserialize a binary tree? A simple approach is pre-order traversal with explicit null markers. During serialization, I write the node value, then serialize left and right children. Null children become a sentinel. During deserialization, I consume tokens in order and rebuild recursively. The null markers make reconstruction unambiguous. Time is O of n, and space is O of n for output plus recursion depth. For production, I would validate malformed input and consider a compact binary format. Be sure to mention traversal choices, null markers, uniqueness of reconstruction, recursive or iterative implementation, complexity, malformed input handling, and trade-offs between readability and compactness. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.